Alright, so in this video we're going to be graphing quadratics in vertex form. So the vertex form of a parabola is y is equal to a times x minus h squared plus k. Alright, so before we even graph any parabola in this form, let's first break down what the a term, the h term, and the k term does to a parabola. And there's a series of transformations from the parent function of y is equal to x squared that we can map on to graph a quadratic in vertex form. So the parent function would be a parabola centered at the origin. The vertex would be at the origin and the graph would be opening upwards. And let's go over the vertical translations for this parent function. So for the vertical translations, so what if you want to make the parent function go up or down? Well, for number one, if you want to graph, say, y is equal to x squared plus 3, then that would be a vertical translation of upwards by 3 units from the parent function. So the vertex just shifts up by 3 points, and every point on the parabola also would shift up by 3 points. And the new graph would be centered at the vertex would be at 0, 3, and the graph would be opening upwards. Same shape, but every point just shifts up by 3 units. And then for the vertical translation moving downwards, for number 2, say we're given to graph y is equal to x squared minus 3. This would be a shift from the parent function down by 3 units. So if you graph it on the coordinate plane, then the vertex shifts down by 3 units. That's negative 1, 2, 3. And the same shape that we had for the original function. All right, so upon adding or subtracting a number from the parent function of x squared, we can undergo some vertical translation moving upwards if you add some number, and a vertical translation of moving downwards if you take away some number from the parent function. That's for the vertical ones. Now for the horizontal translations, so for the vertical translations, the entire function of x squared gets affected, and hence why we have a vertical translation. For the horizontal translations, only the x gets affected. So for number 1, say we're given to graph y is equal to the quantity of x minus 3 being squared. All right, so in this case, only the x's are getting affected. And you might think that the graph would be moving leftwards by 3 units because it's a minus 3. But in reality, the graph is moving right by 3 units. So for any time you have any horizontal translation, it's going to be the opposite symbol of what's happening to the value of x. It's going to be right by 3 if we have an x minus 3 squared. And the vertex of the parabola just shifts right by 3 units along with every other point. So the vertex would be at 1, 2, 3 right there. And the same shape that we had for the original parabolic function. All right, so now for number 2, if you want to shift the graph over, say, left by 3 units, that would be y is equal to the quantity of x plus 3 squared. And that would make the graph shift not right, but left by 3 units. All right, so the same shape of our parabola, but shift the graph left by 1, 2, 3 units. And that's going to be where the parabola's vertex is. All right, so now the vertical translations pretty much tell you what the k term is, which, let me put that over here. So the k term, if it's ever positive, then you have a vertical translation moving upwards. And if k is ever negative, then you have a vertical translation moving downwards. And the horizontal translations have to do with the h term. And if the h term is ever positive, or like if you have a plus x plus 3, then that would be a leftward transformation. And if you ever have an x minus 3 within the argument, then that would be a rightward transformation. Okay, so now let's dive into what the a term tells you. So now the a term tells you 2 things. It tells you what the vertical dilation of the parent function is, as in like would it be narrower or would it be wider? And it tells you the second thing would be if it opens upwards or downwards. So for the a term, for number 1, say we're given to graph y is equal to 2x squared, versus for number 2, so we're given to graph y is equal to 1/2 x squared. All right, so both of these would be dilations imposed on the parent function of y is equal to x squared. So y is equal to x squared, the parent function has an a term of 1. So number 1 would be when the a term increases as it gets bigger and bigger. And number 2 would be as the a term gets smaller. So because 1/2 is less than 1 and 2 is more than 1. So for number 1, if the a term is a 2, or like as the a term gets bigger, then the parabola is going to get narrower and narrower. So let's write that down. The parabola gets narrower, and that graph would look something like this. It's going to be moving closer towards the y-axis. It just gets narrower. So these two parts of the graph just move inwards. Okay, so now if the a term gets less than 1, or like as the a term decreases, the graph is going to get wider. All right, and that would look something like this. And I'm going to exaggerate it a bit. It's not going to look very wide, but it's going to get wider than if the a term was a 1. And it just moves out from the y-axis. Would be the case when the a term is less than 1, or if the a term is decreasing. Now, number 3, say we're given y is equal to negative 1x squared. So now if the a term is ever negative, then that would mean that there is a reflection across the x-axis, which, let me put that down. So this means that we have a reflection across the x-axis if the a term is ever negative, less than 0. So the graph of y equals to negative 1x squared would look like this. It's just going to be the parent function. If you were to reflect that across the x-axis, then the parabola would just be opening downwards, and that would be it. All right, so now let's go through one example which combines all of these different transformations. So say we're given to graph for number 1, y is equal to positive 2 times x minus 3 squared minus 8. All right, so now we know that the form for a parabola in vertex form would be y is equal to a times x minus h quantity squared plus k. And for the function given, so based off of all the different transformations, we know that this graph would be moving right by 3 units. That's what that minus 3 stands for. Is the opposite symbol for the x direction. And this graph would be a translation from the parent function of x squared of rightwards by 3 units. And then the k term is a negative 8. So we would move down by 8 units. Because the k tells you what the vertical translation is, and the h tells you what the horizontal translation is. And we always do the opposite of what the x translation is. You might think it's left by 3, but it's actually right by 3. And the k term is a negative 8, so that's just going to be as is. We shift the graph from the parent function down by units. And just to show you guys what the transformation would be, it's from the origin. If you were to shift right from the origin by 3 units, so 1, 2, 3, and then shift down by 8 units, so it's negative 1, 2, 3, 4, 5, 6, 7, 8. And that's where the vertex ends up being. So we know that the vertex in the vertex form of a parabola would be at h, comma, k. And for the parabola that we have over here, we know that the h term would be a 3, they correspond, and the k term would be a negative 8. So, and that aligns with what the translations are. It's moving right by 3, so it's positive 3. And it's moving down by 8, so it's negative 8. All right, so again, it should be the opposite symbol for the value of x, which we have x minus 3, and that becomes an x, a positive value of x for the vertex, which is a 3. And the y value for the vertex would be the same symbol that we had in the given function, which is a negative 8. So once we know what the vertex for the parabola is, would that be enough for us to graph the entire parabola? No, because a parabola, you would need at least 3 points to graph it. So let's come up with 5 points. It's even better by making a table of values. So to make a table of values for parabolas, let's put the vertex in the exact center of the table of values, 3, negative 8. And then from there, as you increase, as you go up in the number line, then the values increase. So 1 more than 3 would be a 4, and 1 more than 4 would be a 5. So get two values of x that are above 3, and two values of x that are below 3. So 3 minus 1 gives you a 2, and 2 minus 1 gives you a 1. All right, so now keep in mind that the graph would be symmetric about the axis of symmetry. And before we get these y values, let me just graph our vertex. Let's make the coordinate plane over here, and we have 3, -8. So we have 1, 2, 3, 4. I'll go up until 5, and then we have -8. So -1, 2, 3, 4, 5, 6, 7, 8. So 3, -8 would be where the vertex is located. And let's also draw the axis of symmetry, which would be a vertical dashed line going through the x value of the vertex. And this line is imaginary. It's not part of the graph. It's just a guideline. Okay, so from there, we have the vertex, and let's come up with our other 4 points to make it more accurate of a graph. Now, either choose the 5 and the 4, or choose the 2 and the 1. It doesn't matter which one. Since 2 and 1 are more efficient numbers or smaller, let's choose those. So let's get the y value when x is 2 and the y value when x is 1. And let's put the work right here for that. So when x is equal to 1, then you plug in for every x in the given function a 1 to get the y value for it. And y would be equivalent to twice the quantity of x, which is a 1 minus 3 squared minus 8. Now, we know that 1 minus 3 is a -2, and -2 squared gives you a positive 4. So this entire value would be a 4. Twice 4 minus 8 gives you an 8 minus 8, and that would be a 0. All right, so we know that when x is a 1, then y would be a 0. And this point would reflect over the axis of symmetry, meaning that when x is a 5, then y would also be a 0. And why would that be true? Because if you graph 1, 0, which is right here, and if you were to reflect that across the axis of symmetry, then 5, 0 would also be a point on the parabola. All right, so same thing with when x is equal to 2. If you plug that in for the original function, then y would be equivalent to twice the quantity of 2 minus 3 squared minus 8. And now we know that 2 minus 3 is a -1. So -1 squared minus 8 times 2. So -1 squared is a positive 1, and twice 1 gives you a 2. And 2 minus 8 gives you a -6. All right, so when x is a 2, then y would be a -6. And this value also would reflect over the axis of symmetry, which means that when x is a 4, then y is also going to be a -6. And if you graph the 2 points, then we have a 2 -6s, let's see. -1, 2, 3, 4, 5, 6 should be right there. And let's reflect that to plot 4 -6, which would be right here. All right, so once we have our 5 points, then that would be enough for us to graph our parabolic curve. And that is what the curve would look like. Okay, now from there, so we got all the 5 points, which are good enough to graph the parabola. But what if you wanted to get the x-intercepts and the y-intercepts for the parabola? Let's show the work down here. So to ever get the x-intercepts for any graph, it doesn't matter what type of function you have. To ever get the x-intercepts of any function, you would plug in a 0 for the value of y and solve for x. And then to get the y-intercepts for any graph or function, you would plug in a 0 for the vice versa variable of x, and you solve for the y value. All right, so now for the x-intercept, if you were to plug in a 0 for the value of y and solve for x, then we have a 0 is equivalent to twice the quantity of x minus 3 squared minus 8. And now if you solve for the value of x, then you add 8 on both of your sides. And that gives us an 8 is equivalent to twice the quantity of x minus 3 squared. And these are gone. So from there you would divide by 2. And that gives us a 4 would be equivalent to the quantity of x minus 3 being squared. And the inverse of squaring would be square rooting both of your sides to get rid of the squared. And down comes your x minus 3, which would be positive or -2. Right, so never forget to put down positive or negative every time you square root any number in quadratics. And then you add 3 to get the value of x isolated. And that gives you an x value of either positive or -2 plus 3. And that would break them into 2 solutions. The first one being either a 2 plus 3 or the second one being a negative 2 plus 3. So in the first case, 2 and 3 gives you a 5, and in the second case, negative 2 plus 3 gives you a positive 1. And that means that so we plugged in a y value of 0 to obtain these values of x, and these correspond to the points of when x is a 5, then y is a 0, or when x is a 1, then y is also a 0. So this parabola has two x-intercepts, which I believe we graphed them already with the table of values. 5, 0 is right here, and 1, 0 is right there. All right, so now let's move on to the y-intercepts. So you want to plug in a 0 for the value of x to get the y-intercept for the function. And so we have y is equivalent to twice the quantity of 0 minus 3 squared. And then we have a minus 8. All right, so now from there you want to solve for y using PEMDAS, and that gives us a twice the quantity of 0 minus 3 is a negative 3, and negative 3 squared gives you a positive 9, and then minus 8. And that gives us a twice 9 is 18, and 18 minus 8 gives you back a 10. So we obtained the y value of 10 upon plugging in a 0 for the value of x. So this y-intercept corresponds to the point 0, 10. And let's just plot that as well, because I don't think we have that point plotted. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which goes right off the chart. And that would be the graph of our parabolic function in vertex form with 5 points along with the x-intercepts and the y-intercepts. All right, so that's number one. Let's go over one more example to solidify the information. So now we're given for number two to graph y is equal to negative 3 times x plus 1 quantity squared plus 12. All right, so now we know that from our transformations that this graph would be the result of shifting over the parent function left by 1 unit and up by 12 units, right? So the opposite symbol for the x direction, which you might think it's right by 1, but it's actually left by 1. And the actual symbol for the y direction, which is it's a positive 12, so you move up by 12. And if you write this in the proper form for the vertex form of a parabola, which is y is equal to a times x minus h squared plus k. Notice how we don't have an x minus 1 over here, we have an x plus 1, right? So if you rewrite this in the proper form of the vertex form of a parabola, then this would be y is equal to negative 3, so a aligns with negative 3, and then times x minus the quantity of negative 1 being squared, and then k would be a 12. All right, so we can see that if you write it in the form of x minus h, then a double negative does give us an overall positive symbol, and they're both the same functions. They maintain value, but we shifted it over in such a way that we can tell what the value of h is, and h is not a positive 1, h is actually a negative 1 if you write it in the proper form. So we know that the vertex would be at hk, and that corresponds to negative 1, 12. All right, so again, h is a negative 1 and k is a positive 12. So the opposite symbol of the x direction for the value of x for the vertex, and the actual symbol for the y value for the vertex, and that's going to be the vertex. Now from there, it's the same process. You want to get the table of values, and before that, let me just graph, or let me set up the graph for this parabola. So we have negative 1, 12. And so we have negative 1 is right here, which let me put more points. I'll go up until negative 3, and then we have negative 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be right here. All right, so the scale is a bit off, but that's where the point would be. Now, from here, you want to come up with more points, because 1 point's not sufficient for us to graph the problem. So if you make a table of values, keeping the negative 1, 12 in the center of the table of values, then you want to come up with more points. So if we increase negative 1 by 1, that gives us a 0. Then increase 0 by 1 again, which gives us a 1. And then if you go 2 values below negative 1, that's negative 2 and negative 3. All right, so for this, we'll choose 1 and 0 because they're easier numbers to plug in. So if you plug in an x value of 1, then we have y is defined, y would be negative 3 times 1 plus 1 quantity squared plus 12. All right, and that comes out to be negative 3 times, so 1 plus 1 would be a 2, and 2 squared gives you a 4, so that's going to be a 4. And then we have a plus 12 at the very end. And that gives us a negative 12 plus 12, which would be a 0. So y would be a 0. When x is a 1, then y would be a 0, which let's make that a point right here. And this y value would reflect over the axis of symmetry, which let's put it down here. So if 1, 0 is a point, then so would negative 3, 0 also be a point on the parabola based off of our axis of symmetry. And now from there, if you plug in an x value of 0, let's check what the y value for that would be. So we have y is equal to, negative 3 times 0 plus 1 squared plus 12. And that gives us a negative 3 times 0 plus 1 is a 1, and 1 squared is a 1 still. Then plus 12, and that gives us a negative 3 plus 12, which comes out to be a 9. All right, so when x is 0, then y would be a 9. And this point would reflect over the axis of symmetry once again. And so if 0, 9 is a point, which let's graph that. 1, 2, 3, 4, 5, 6, 7, 8, 9. If 0, 9 is a point on the curve, then so would negative 2, 9 be a point on the curve as well. And that would be right there. All right, so again, the scale is a bit off for this, but that's what the approximate graph would look like. And if you connect all the 5 points, then that's going to be our graph of our parabola. All right, so from here, let's just get the x-intercepts and the y-intercepts. I believe we already got the x-intercepts, which would be a 1, 0 and a negative 3, 0. And let's just get the y-intercept quickly. All right, I think we got that as well. That's 0, 9. So this would be the y-intercept. That's 0, 9. And if we didn't already get the y-intercept using our table of values, then you would plug in a 0 for every x and solve for the y value to obtain the y-intercept. And we got the x-intercepts to be the 1, 0 point and the negative 3, 0 point. So again, if we didn't have these points on the table of values, we just happen to have them. But if we didn't have them on the table of values, then you would go on ahead to plugging in a 0 for the y value and solve for the values of x, and those would be the x-intercepts.